have a converter. The converter is single phase AC. So this is AC, which is single phase. And then we want to convert to output. Output also AC, single phase. And we want to convert the power from the input side to the output side. So we have two switches, switch 1 and switch 2. So this is current sink. So you can see the current can go this way or the current can go this way. So according to our rules, the output current cannot be interrupted. So this line Q1 plus Q2 should be equal to 1. So this is the general rule. If Q1 plus Q2 more than 1, then short circuit. If Q1 plus Q2 becomes 0, then the output current open circuit. So the rule is Q1 plus Q2 must be equal to 1. So problem A, please draw the circuit. So input is AC, output is AC. So the switch must be AC, otherwise you cannot transfer energy. So which means this is AC switch 1, AC switch 2. So how can we create AC switch? So this is AC switch. This is equal to AC switch. This is also equal to another AC switch. So if you have current go this way, then the electrical diode go to the output. If you have current go another way, then you can go from output to here, and then go to diode or to input. So you can see, if you use this one, if Q1 and the T1 on, then go this way. If Q2 and the T2 on, then go this way. So the switch is AC switch. And if we check this one, if Q1 and the T1 turn on, we can go this way. If Q2 and the T2 turn on, we can go this way. So the current can go this way or this way. So we call it is AC switch. If you want to realize the circuit, you should do this. So in general, currently, some company manufacture two switch together, become one AC switch. So you can easily buy one AC switch from this company. Okay, so the first question for the circuit. The second question, the frequency of Q1 is 10 kilohertz. So this is 10 kilohertz. The output average power is PAV. So we transfer output power PAVE. What is the amplitude of the 60 Hertz Fourier component of the input current? So here we have voltage like this. So now we want to transfer energy to output. We don't know the real current, but the real current has fundamental and harmonics, right? If you want to transfer power, what is the most important? Fundamental. So we hope the current could be like this, right? The other is harmonics. But harmonics is so small, so we just neglect it. But sometimes the current is not so good. Sometimes we cause delay. So this is V in. And our current could be like this. So we have phase angle, phase difference. It is possible. But this is Fourier series. This is also Fourier series. But we don't know the angle. We don't know the phase angle. So now the frequency is 10 kilohertz and the input is 60 hertz. So we use the switch to convert the input power into the output power. So we know V in is equal to amplitude, input amplitude. In general, it could be 110 RMS. So the amplitude is like this, 145. This is a cosine 2 pi. This should be F. But we know input is 60 hertz. So we just put 60 hertz. And we don't know the phase angle, because we don't know where is the zero. Zero could be here, could be here. So we can say we have a phase theta V. So we can rewrite V in here. And then we have input current. The input current is like this or this. So the input current has phase, the amplitude, and also the phase. The phase could be different from voltage. So like this. The voltage phase and the current phase are different. So this is theta V, this is theta I. So theta V is not always equal to theta I. So we call this is power factor or phase shift between the voltage and the current. So if switch 1 on, what is the output? Output is V in multiplied by Q1. If switch 2 turn on, then what happens? Output is Q2 multiplied by 0. Here is 0. So from equation 3 and equation 4, we can write the output. The output is V in Q1 plus 0 Q2. So here, V in Q1 plus V2 Q2 0. If Q1 is 1, then output is in. If Q1 is 0, Q2 is 1, then output is 0. So output can switch from V in and 0. However, this is always 0. So we can neglect this. So output is Q1 V in. So we have midterm exam, April 13, and it is open book. You can bring calculator, but no computer, no cell phone. So the time is. So now we can assume that the circuit is lossless, because this is ideal switch. This is ideal switch. If it is ideal switch, what is the loss? 0, right? We neglect the switching loss and the conduction loss. Then the total input power equals to the total output power. So P in equal to P out. All of them are P average. So the input average power, what is the input average power? The waveform is like this. So what is this power? This power is voltage multiplied by current multiplied by cosine theta V minus theta I, right? So you can see this is amplitude. So if you calculate power, this should be RMS, root mean square voltage, right? So it is amplitude divided by square root 2. this is current amplitude. So the current RMS should be amplitude divided by square root 2. So VI cosine theta V minus theta I. This is input power, right? What is output power? Output power is PAVE. So this is output power. So input power equals to output power. Then we can calculate this one and we can compute the input current. So this is the circuit, and we can use the switch to do what? Do the phase shift. If we make the voltage and the current in phase, then cosine theta V minus theta I become cosine 0. If cosine 0 it is 1, then we call this is power factor correction. Because the power factor, the phase shift is 0. Power factor is 1. 1 is perfect. We cannot over 1, right? So this is perfect. So we can say we can use the switch to improve the power factor. And also we can use the switch to change output amplitude, right? You can see we can use the switch to change output amplitude, right? So we can do the power factor correction. We can convert the output, we can change the output voltage. So this is the problem 1. Do you have any question about problem 1? Any question about this? Okay, if no question, then it is good. Then we move to the second problem. Okay, now we move to the second problem. So here we have AC to DC. So we have AC to DC. So we have A phase, we have B phase, we have C phase. So VA, VB, VC. And we call this is minus, plus, minus, plus, and a minus, plus. So we have 3 phases. So this is ground. And then we have a switch. SA, SB, SC, 3 switch. And then we have output. So we have output. So it's V out. So output is current shift. So this is I out. So this is 3-phase AC to DC converter. This is a 3-phase AC to DC converter. So now it says VA equal to VO cosine omega t. VB equal to VO cosine omega t minus 2/3 pi. And the VC equal to VO cosine omega t plus 2/3 pi. So the equation 1 plus V out B. Compute average of V out. C. Please draw the switching function of SA. So we have 3 matrices. So we know this is 3-phase AC to DC converter, or we can call it is 3-phase AC to DC rectifier. So it is 3-phase AC to DC rectifier. So now we try to solve the problem. So first we have ADC voltage. So we have A phase. So we have A phase. And we have B phase. B phase will be here. So this is A phase. This is B phase. We have C phase. So we have C phase. So C phase will be here. Okay. C phase will be here. And then we have C phase. Okay. C phase. So we have the 3-phase waveform. Now we know this one is here, this one is 30 degrees, this one is 30 degrees. So this one total is 60 degrees. From here to here. And first, what is V out? So only the maximum voltage can turn on. So we can understand the V out. So what is V out? V out is like this. So this is V out, because only the maximum can turn on. If the maximum turn on, the other 2 phases should be turned off. So this is V out. Okay. Then what is the average of the V out? And what is the switching function of A phase? So VA turn on here. So you can understand this is SA. So here SA is 1, then SA becomes 0, and then until here, then this is VA again. So SA turn on again, like this. So how about SB? B phase turn on here. So SB turn on here, and then turn off here, and then become 0, 0, and then turn on again. How about SC? So we can see this is SC. So SC turn on here, and here, and then turn off. So SA, SB, SC, right? So we know SA, SB, SC, and what is V out? SAVA plus SPVB plus SCVC. So what is V out? So here SA turn on. So V out is copy VA. So here VB turn out, V out is equal to VB. Here VC turn on, V out is equal to VC. And then VA, VB, VC. So VA, VB, VC, VA, VB, VC. So this is V out. So we can easily compute, and the amplitude is VO. The peak value is VO. The peak value is VO. So now we want to ask what is the average. So we want to compute the average. So what is average? Average. So we can take from here to here, here to here. So we call this is one period, one T. We also can calculate from here to here, but the answer is the same, right? So we only need to calculate one time. So because this is symmetric here, symmetric. So you can calculate a full period. You also can calculate a half period because it is symmetric. So from here you get the answer. From here you get the same answer. Okay, so what can we do? And we can say we have to calculate one period. But one period is too long. We also can calculate half period from here. So we also can calculate half period. Okay, so we can get this is 2t, this is 0 to half t. This is V out T dt. Okay, so this is what is T? T is from here to here, 120 degrees, or we call 2/3 pi. So 1, 2, 3 become 2 pi. So 1t is 2 divided by 3 pi. Because from here become 2 pi. So we only occupy 1/3. So it is 2 pi divided by 3. So we can put t equal to 2 pi. T equal to 2 pi. Oh, no. T equal to 2 pi divided by 3. So here we have t, so t is 2 pi divided by 3. And how about here? Half t, so only pi divided by 3. And how about V out? V all cosine theta d theta. So this is V all cosine theta. So the waveform is V all cosine theta. Okay, then we can calculate this value. So it is 3 pi V O, and then we can get sine theta. Okay, and then we can get 3 pi V O. This is sine theta minus sine 0. Then we can get 3 pi V O square root 2, square root 3 divided by 2. Then we can get 3 square root 3, 2 pi V O. We can get 0.627 V O. Then we finish. Okay, so you can compute the average easily. So do you have any question about question 2?
So how we get 120 degrees?
This one, you can see we have A phase, B phase, C phase, and A phase. So this is T. And we have here, and then we go back to here, the same point. So this is sine wave. For one period, it is 2 times. But we have 3 times. So each time, 2 times divided by 3. Okay, so you can use your eyes to identify the relationship. Okay, so do you have any question? Okay, so if no question, then we finish question 2. So I think our midterm exam is similar to this. Very simple, but you have to understand, fully understand. Then you can easily do the simple math. Okay. So do you have any question about our midterm exam? So our midterm exam is April 13, start at 9:10 in this room. So it is in our room, this room. And we will be open book. So you can bring your notes, your book, and your assignment, everything. And a calculator, because you need to calculate. But you cannot use computer to search. You cannot use cell phone to search. Okay. So do you have any question about the fundamental rules?
How many questions we have to attempt in middle term?
Ask me.
How many questions we have to attempt in middle term?
Middle term, as far as I remember, the middle term is 35, and the final exam is 35. Assignment is 30.
How many questions?
I think 5 questions. Okay? Okay, so now we can go to the video and we can watch the video. So anyone can help another student to get back his assignment. So if you know anyone who didn't attend, you can help him to get the assignment back. Also,
Last time we saw the type of power factors and all the basic stuff related to that. Now we'll check the power factor correction methods used in the power supplies. So let's go for a ride. If you see the circuit diagram of a power supply, there is a bridge rectifier at the input, which rectifies the AC input voltage. Then this rectified voltage is provided to the DC link capacitor, which filters the AC component present in the voltage
we use
and
rectifier
passes
here.
the DC voltage to the regulator or
Convert AC to DC.
converter. And this DC to DC converter gives required DC output.
And then
We have seen many
we
ways to
can
increase
use
the
buck
efficiency of
converter
this DC to DC
to
converter
reduce the
to
DC
get
voltage.
and reliable output power. Now it's time to take care of this rectification block.
So now we focus on this
So far we
one.
have seen how the voltage behaves and we get the DC output. But
How can
if
we
you
convert
check
AC
at
to
the
DC?
input, it goes like this.
So now we
The
have,
voltage is sinusoidal,
current go
but
this way.
current is full of
but the
distortion.
current is not good.
And this
Voltage
happens
is good,
because of this
current is
capacitor.
not good.
This capacitor charges quickly at the peak of the
You can
input
see the
voltage.
current is like this.
Charges
It is discontinuous.
current flowing
It
through the
is not
circuit
a
is
sinusoidal
called linear.
waveform.
And there are multiple harmonics present in this current wave.
So it is multiple harmonics. So the
So because
harmonics
of that,
is very
we get
serious.
the inefficient power factor from the electronic appliance.
So it is inefficient.
And this
power
type of power
factor.
factor is known as harmonic power factor.
So we see harmonic
What
power
about the
factor.
basic concept of power factors? Watch my previous video. I have attached the link of that video in the description. You can click on this card above.
So now we need to
This
improve
distortion of
the
the
power
current
factor.
waveform returns back to the power grid, which reduces the efficiency of the grid and can cost us heavy penalties in the electricity bill. So to avoid such things, there are particular standard rules to limit the
So there are
harmonic
some
distortions
standard
in
rules
order to get the
to
good power
limit
factor
the harmonic
of the
distortion. To get good power
And these
factor.
are divided into different classes, which are known as Class A, Class B.
So now we
Class
divided to different load A, B, C, D.
Here, all the household equipments which consume power more than 600 watts, like audio equipment, cooking
600
appliances,
watt.
coolers, etc., are categorized. All the portable tools which are not professional, like arc welding tool, come into this category. All the lighting loads, like LED lighting
Lighting
and
load also
street lighting
need
or other lighting
regulation.
loads, come into this class.
So this is
The
C,
equipment
class
which
C.
consumes 600 watts
This is
of power,
class B.
and those
This
are
is
that
class A.
come into this category. So all the televisions,
TV, class B.
computers, laptop chargers
Computer,
are
class
class
B.
B type of loads. Only those loads which consume more than 75 watts of power and run on the current below 15 amperes come in these classes. And there are different type of power factor regulation requirements
So we have
related to current
different
harmonics
regulation
of each
for
class.
different class.
To avoid the loss in the power and improve this power factor, we need to use power factor correction.
So now we need to use power factor correction
The power factor, the waveform of the voltage
to improve
and
the
current should be
waveform
identical,
of the voltage
so that
and the
we get the
current
maximum power
like this.
every instance.
We need a sinusoidal voltage,
This power factor
sinusoidal
correction
current.
technique is divided into two parts. First is the passive power factor correction,
So we have
and
two
second
parts,
is the
passive
active power factor
power
correction.
factor correction and the
In
active
passive
power
PLC
factor
method,
correction.
the passive components like inductors
So
take care of
passive
the
power
power factor.
factor correction. Inductors,
PLC inductors are
So we
connected
use
like
inductor.
this with the power supply line.
but it
But there are
is too
some
complicated.
disadvantages
And
of
the
this
inductor
type
is
of
very
factor
huge.
correction technique, despite of having small and easy circuit. First, the inductors which are used in this application are so big and heavy
Heavy,
because the
inductor is
frequency
heavy.
which we are dealing here is in just a few hertz. All over the world, the voltage supplied by the grid is not same. For example, in India, it is 230 volts AC
India.
frequency of 50 hertz.
130 volt,
And in US or
50
Canada,
hertz.
it is 110 volts,
110
frequency of 60
and
hertz.
60 hertz.
So we cannot use the same inductors
So
in
we
both
cannot
countries.
use the same
For that,
inductors.
we have to
for
add a
both
switch
countries.
for universal usage. This switch arrangement will be different if you are using a particular equipment in the US, and it will be different for the same equipment if you are using it in the India. Well, if somebody doesn't know how to use it, that guy will end up destroying this power supply. And the power factor correction efficiency of this passive PFC is very poor. So to avoid these disadvantages, we'll jump to the active PFC technique.
So passive is very poor.
Popular type of this
So we
is
prefer to
boost
use
PFC.
active power factor correction.
So the boost DC to DC
Active
cable
power factor
is
correction.
used between rectifier and the filter capacitor. After the full bridge rectifier, the boost inductor is connected
So
in
now we
series.
use boost.
Then an active switch, that is
So
MOSFET,
we use
and
switch,
passive switch,
MOSFET,
fast switching
diode.
diode is used.
so we call this is active.
DC capacitor is used to filter the ripple present in the voltage. The voltage at the inductor is rectified sinusoidal input. So the average current flowing through this circuit should also be like this.
So we hope
To do
the
so,
voltage and the current
MOSFET
in
is
phase.
accordingly by providing the PWM signals
So we
different
control the
cycles
first switch
such a way
modulation
that the current
to
in the
make the
circuit
voltage and the current in phase. Then the input, we have voltage and the current like this.
at the input,
So it is
current will be
unity
full cycle,
of factor
just like
because
voltage.
the phase shift is zero.
To control the flow of current, we need to add a closed loop feedback system.
However, we need a lot of
The
circuit.
control logic will take
We
the
need a MOSFET,
input
we need an
voltage,
inductor,
feedback of the
and
current
we need a voltage sensor. So we have to
because the
detect
same current
voltage
is flowing
here.
to the whole circuit. So the input voltage
So
is
input
referenced,
voltage
and by
should be
referring to it,
detected.
the current of the circuit is adjusted. Well, the current can be controlled, but we need to control
Now we
the
want to
output
control
as
the
well.
current to be sinusoidal.
The load in our case is DC to DC converter, and it will have different input voltage and current requirements. So the output voltage of this PFC boost
So
converter
we also need to
should
feedback
also be
output
adjusted.
voltage. This is the desired output
So we need
voltage,
to take the feedback
real
of
output
this
voltage. Then we
as
can
well.
create voltage
This
error,
voltage is then compared to the reference voltage.
and then we use a PI
at
controller.
the input stage. So the comparator gives the error output of
So
this
this is
signal
the error
at reference.
between reference and the real output.
This error signal is provided to the one of the inputs of a multiplier.
Then we use
This input is
multiplier.
multiplied with the original input voltage reference. These both signals get multiplied and the output of the multiplier goes to the comparator, which
So we have
compares this
comparator.
multiplied reference signals
This is
and the
real
current flow to
current.
the circuit.
This is desired current.
Then this comparator
Compare it
takes the decision to
Then we
provide
design
pulse to
controller
this MOSFET.
to
By
control
controlling
the
the switching
MOSFET.
of this MOSFET, it supplies the required voltage to the DC to DC converter and controls the behavior of the circuit current.
Now we can control
This
the
process
current like
operates in
this,
cycle.
and then we can
This is
get
how
unity power
classic
factor.
power factor correction method works. There are different controlling techniques to do so, and this controlling of the current is categorized as continuous conduction mode,
So we have continuous
critical
conduction mode,
mode.
critical conduction
The
mode.
of all these controlling methods is the same, only the difference is the behavior of current and its controlling strategy.
So we can control different ways
If we
for
take
the
the
current.
continuous conduction mode, the current of the inductor doesn't go to zero.
So this is
Follows
voltage.
the voltage.
Now we follow the voltage
Ripple of the
to
inductor
create
current
current.
is very low. So the value
current
of this
is like
is
this.
very high and the design gets bulkier. But this type of control strategy is very helpful for high power applications.
Very helpful for high power application.
Now let's
High
check
power.
the critical conduction mode. The
And
ripple
then
of the
critical
inductor current
conduction
is
mode.
very high. The inductor current starts
It is
from
like
zero
this. So
and
the current is
increases up to its maximum
discontinuous. It is not
As soon
continuous.
as it reaches to its maximum
Discontinuous.
value,
Go back
it
to
falls to
zero.
zero again.
Then go to the voltage and then to zero.
Process.
So you can see this is the
This
real current.
is the sinusoidal structure. So
But the fundamental still
we have
sinusoidal.
got SR flip-flop and a zero detector in the controlling logic.
So
which
we
detects the
use
zero crossing of the current
free flow
and the
to
switching
control
of
the
MOSFET
switch.
is controlled by SR flip-flop.
Then we can obtain
So
this
as the
waveform.
MOSFET turns on, the current increases and goes up to higher level. And the SR flip-flop resets the
We call
current
this is
when it
SR
reaches to its
flip-flop.
peak value. So the current falls down again. The average of this
So the
current
current is like
is
this.
sinusoidal.
To the voltage,
This
go
type of
zero,
controlling
voltage,
method
go
is
zero.
very
So fundamental is like
Although the
this.
size of inductor is very low in this technique, but it has very high conduction losses.
But
So
a
this
high
method
conduction
is not
losses.
suitable for high power applications.
So this is only for low power, not for high
Well,
power.
that's it about the power factor correction technique. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.
Okay, so we can watch the next video. This is for power factor controller. Now we go to the next one. Passive power factor correction. Not use the switching device, use inductance or transformer. We call passive. So this is multi-bus converter or passive power factor correction.
Welcome to our advanced power electronics and control courses in NPTEL. We shall continue with the multi-bus
Multi-bus
converter.
converter.
Now, let us consider we have
So it is
already discussed
12-bus converter.
12-bus converter. Now let us take the
It is like this. So we have transformer. Here is transformer. But the transformer is a special transformer because the phase shift is minus 23 or 23.
So the phase difference between this transformer required to be actually
23. So we call it is a special transformer.
Special control transformer is required to be built to fit to the
We call it
system.
is zigzag transformer.
Transformer is called
Zigzag
zigzag
transformer.
transformer. So we shall see that, and IA is basically we will have this component IA prime plus delta
Zigzag
prime
or
plus
phase
bar.
shift transformer.
This is the IA, this is IA delta and IA bar. This is the 3 current in secondary.
IA minus,
So this consists
IA
of the
minus.
and this side is basically primary side is IA and which is actually star current. So
So you can
what
see
happens in case of
if
the
we plus IA,
impulse converter?
IA minus IA
There
plus,
are
it
3
is
currents.
close to sinusoidal. So we use transformer to make
One by U,
the input current.
other
Near
by
sinusoidal.
dot.
We only use transformer.
So these 3 current consisting of actually the current of the individual rectifier.
So
And if
after
you
we use
superimpose these 3
transformer,
current,
the current harmonics only 3%.
the current
The current like this. No switch.
and individual THD of this current may be as high as 23%, but when it is been reflected to the primary side, so values are
Only
found
3%.
to be less than 3%.
So like this, we can get
We have
the
a
input
water
current
quality issue.
very similar.
IEEE
Sinusoid.
519 standard. So that says that THD is required to be 5%, so we can achieve it.
We can achieve by using
Thus,
transformer
what happened?
to obtain
So it
low
doesn't have
current
any
harmonics.
6n plus minus 1 harmonic, 12n plus minus 1 harmonic, it starts from 18n plus minus 1 harmonic. So lowest harmonic actually after first harmonic will be 17, and thus line THD comes out to be only 3%.
So 3%.
So this is few waveforms
So
of the
we can use
16 bars
1,
converter.
2, 3
So,
together, and the summation become this current.
delta.
This is very similar to a
Impose this
sinusoidal
together.
current waveform. Then we can improve the harmonics and the power factor.
And this is the harmonic spectrum, the real data.
So you can see this is very close to sinusoidal current waveform.
Of the primary of this 18%. Similarly, same analysis can be continued as we have done in case of this actually the 6 and 18 harmonics. So you can see that by increasing the, if it is a low load current, of course THD is going to be higher. So once actually come down to the 3% or zero
3%
source
out
inductance,
of
and it can
3%.
be much below to the almost actually 0%,
But we only use transformer.
0.1
No.
per unit of the
MOSFET, no IGBT. So we call it is K-set, power factor correction.
power factor and low input current, and gradually it will decrease little bit. But power factor, you can see that the difference is not much. So we accept power factor, most of the power quality companies and utility accept power quality in and around 0.95. So they are actually well in the range, and in source impedance is 0, and they are well in the range of the 0.98. So thus this should actually suits all our purposes for practical utilities as concerned for rectification operation. So now let us talk
So
about
now we have 24 plus
24 parts diagram.
G, 1, 2, 3, 4. The phase shifter,
Even though it
15
almost
degree.
makes, but we feel some
So
application will
the total becomes
very
this.
precise kind of actually power factor and other issues. So similarly, so we
We
require
have to
24
use
percent water.
zigzag transformer.
There this actually zigzag transformer was shifted
So you can see the input current like this,
20 degree. Here it is
1.5%, very close to sinusoid.
because it is a 24%.
However, the transformer should be carefully designed.
This will have a shifted by delta. This is a star, so this star and star will have a shift phase. And from there we will have actually minus 15 degree phase shift. And this will have this zigzag transformer will have a plus 15 degree phase shift. Thereafter we have a delta.
This is
That
Y,
actually
this is
will be
delta,
30 degree.
this is zigzag.
So you have actually, let us draw this current because we can not draw all the current in together. Let us draw basically.
And finally, the
This
input
current.
current is perfect,
This
very
current
close
should
to
be
sinusoid.
on
The
it.
harmonic only 1.5%.
This current and this current are having a 15 degree phase shift. Similarly, this current and this current will have a 15 degree phase shift. They are put together. And all these two currents are then put together into the third waveform. And this is consisting of this
So
basically
the
primary
KT
current,
only
and that is basically
1.5%.
Ia plus Ia delta plus Ia bar plus Ia prime. So you can see that these individual THDs are 24%.
Each one are
But
very huge,
once you come
but they can cancel each other. Finally, the input current becomes sinusoid.
This load current becomes basically, and we have a harmonic to be shifted at the level of the 23th harmonic. So the THD level will be very low as 1.49%. So this is the advantage of this actually. The 24 pulse converter. Now same thing. So if you have a low source inductance or zero source inductance, so your THD will gradually come down. But you can see that it starts from actually 6% and goes below 2%. And similarly, you can see that what happened to the power factor. Power factor is quite good, and for the A, power factor is as close to the
Power factor is 98.98.
Now, dual pulse separate type tied with 20.
So this is 12 pulse.
This kind of thing. So this is a separate. You have a one started topology and one.
So we can have 20 minutes break and we will start next class. So we have 20 minutes break.